So we're going to have to keep the science very exciting, and we're going to talk about discovering our origins today. Here are the fundamental questions that we're going to attack with the Origins Space Telescope. These are the kinds of questions you can bring home to your mom and tell her what you're working on. These are things everyone who's ever been alive has wondered about at some point in time. These are questions that we've all asked at some point in time, and these are the things that Origins is going to attack. So the first one is, how does the universe work? How do we get here? Are we alone? And the discovery of new phenomena. So answering these profoundly important questions is enabled by a crazy sensitivity improvement with Origins. Factor of 1,000, have to kind of look at that again and again and remind myself it's actually 1,000. This is the equivalent of going from having no telescope to having our very first telescope. So the kind of discovery space and parameter space that you're opening up is, it hasn't been done before for a very long time, and I'm very excited to see what that will achieve. And it's all done in a very low risk, very simple design, highly achievable. Have a 5.9 meter aperture, non-deployed, low risk development, costing and testing, and you're looking at 3 orders of magnitude in wavelength coverage. Sounds almost too good to be true. We will explain how it is not too good to be true and how it is hopefully going to be a reality. So my name is Cara Battersby. I'm part of the Science and Technology Definition team for Origins, but I'm not just representing the work that I personally have done. This is obviously the work of many people, and the mission design that we're going to share with you today is something that was driven by the community of astrophysics. This is what people have decided. These are the most important questions. These are the things we want to be pursuing, and we've designed a mission around that to answer those important questions. There are 4 major mission concepts being put forward for the decadal, going from the infrared to X-ray. HabEx looks at habitable exoplanets, and LUVOIR, UV optical and infrared. Origins is the only infrared telescope in here, the really true infrared telescope. But people always say, well, James Webb is an infrared telescope, so therefore, why do we need Origins? Well, infrared has a branding problem because the infrared spans 3 orders of magnitude in wavelength, but only gets one name. UV, 1 order of magnitude. Optical, 1 order of magnitude. Origins, 3 orders of magnitude, same name as James Webb. That's what you call a branding problem. Obviously, there's no real problem, just a branding problem. So hopefully I can convince you all that the infrared, the far infrared, is worth pursuing with Origins. So to give you a sense of where this huge increase in sensitivity comes from, I want to start by looking at telescopes in the recent past over the wavelength range of Origins from about 3 to 600 microns. So shown here is the fundamental astrophysical background, as this darker red line here at 4.5 Kelvin, and then various telescope temperatures that have come before and the background level that they are able to achieve. And now we have plotted on top these different background levels. And so James Webb, you can see, will really push to this background level here, but then in the far infrared, we have a huge parameter space, this 3 orders of magnitude that I was talking about, that we have yet to probe, and Origins will reach that astrophysical background limit and push us down to that factor of 1,000 improvement in sensitivity. Wow, so cool. Also means it can't really get any better than this, right? How many other missions can we think of that you're like, you can't imagine anything that could be better? This is pretty much as good as it gets. All of this with minimal deployments. We have 4 deployments that will happen on Origins. You're going to watch each of them here. 3 of them have already been done before, rigorously tested, used in previous spacecraft. The one that hasn't been is the sun shield expansion, which you'll see in a minute. And this is a very simple 2-spring mechanism, basically like opening up a pop-up tent. So you can see it's going to spring out, and then it'll pop up. And you have your single primary mirror here and your secondary there. So it has the collecting area of the James Webb Space Telescope, but it's actually a single mirror. So there's no deployment of the mirror. There's no complicated deployments. All these deployments are extremely simple. And you can see our pop-up tent sun shield here opening up. So these crazy improvements in sensitivity are enabled by having your colder telescope And so we can use something that's a very simple design, tried and true, and still get this revolutionary change in sensitivity. That's the power of origins. Here's a more detailed picture of the telescope where you can see the inside of it as well. As I mentioned before, the diameter is 5.9 meters. That's the same area as the James Webb Space Telescope. Reach a diffraction limit at 30 microns. We have long life cryo coolers. It's built for a 10-year. It's a 10-year propellant, and the mission is also designed to be serviceable. This observatory is also designed to be very agile, so very quick mapping speeds. The instruments that we've designed that I'm going to describe in a minute here, they're all designed to be highly adaptable, because when you're opening up this kind of discovery space, you don't walk into it and say, I know exactly what's going to happen in here. You plan for the things that you know are going to happen, but if you don't have your eyes open for the new discoveries, then what's the point of doing this incredibly increase in sensitivity? So all of this is just built to be highly adaptable, and we'll be at an L2 orbit. Okay, so the three instruments that we have were decided after much discussion, and we have several upscope options as well, but these are the ones that are for the key science goals that we've designed for this mission, and also, as I said, designed to be highly adaptable for the future questions that we don't know yet. These instruments are the Origin Survey Spectrometer, which covers a huge range in the far infrared. This low resolution mode here will be the powerhouse for large spectral line surveys of galaxies across cosmic time, but you also have higher spectral resolution mode for specific science cases. We have our far infrared imager and polarimeter at 2 bands, 50 and 250 microns, which can do large area survey mapping incredibly efficiently, and also polarization. And finally, we have our mid-infrared spectrometer camera that's used for planet transits. This is what will enable us to look for biosignatures towards other potentially habitable planets. And so this is designed to be ultra stable, and this will enable us to make that final leap forward to being able to definitively detect or not detect biosignatures around other planets. And this operates in the mid-infrared range continuously from 2.8 to 20 microns. The continuously is important, as you'll see soon. So Origins builds on a long heritage of missions and is able to take advantage of a lot of the testing facilities that we've used. This means that it should be very easy. We have a clear plan of how to move forward with Origins and all of the steps to take. And in this case, this is looking at the test as you fly option. So I learned yesterday that not every telescope that goes into space gets to be tested as it flies. Origins is special in this way that it gets to be tested as it flies because we can reuse chamber A from James Webb Space Telescope. So it's there, it's ready for us. We can just put Origins in tomorrow. If we had it tomorrow, if anyone has a wizard that they know that can just build it tonight, we could test it tomorrow. So now I'm going to talk about some of the technological challenges to building Origins. And you'll notice this is actually the only slide that we'll have about it. So we don't have slides talking about the deployment of your telescope or the deployment of some complicated sun shield. Everything else about the architecture of the telescope is been tested. It's very low risk and it's very robust. So these are the only things that are considered things that require substantial work before we'd be able to fly. So if your wizard friend is going to build Origins tonight, these are the things your wizard friend may want to consider. But this is really it. So the two main things are detectors and the cryocoolers. So the detectors in the far infrared, we need to really just push down to this really low sensitivity limit. And if you look at the noise equivalent power as a function of time, you can see this really nice trend going downwards, and this green line is the level that we need to reach. If you look at the timeline here, we think it's very feasible that we should be able to reach that milestone long before Origins would be being built. And in fact, there's one example of one technology that does this. And so we're investigating other technologies. And so the real big challenge is all about multiplexing this. It seems like achieving that sensitivity is very highly feasible, but multiplexing is sort of what we're working towards. In the mid-infrared, the main challenge is just reaching these very low, this very high stability, this very low parts per million. We want to reach 5 parts per million. And again, this is what enables those biosignatures. If you want to see if your friend ET made it back to his home planet, and you have to be able to get that noise floor down to 5 parts per million. So we're investigating a couple of different technologies that seem very promising for this moving forwards. Cryocoolers are in hand. We can get to 4.5 Kelvin already, thanks to Hitomi and James Webb. And now just working on the 50 millikelvin on the detectors themselves is something that NASA is working on right now. But that's it. This is it. This is what we have to do to make Origins work. I think if we put our heads together, this is something we can achieve. We have a clear mission development timeline that starts in earnest around 2025 in phase A, and then launches in 2035. This is a very quick timeline, but also, again, very feasible because of the robust architecture and the fact that we're relying on the heritage of so many previous facilities. This short time for testing is, again, because we have a lot of the testing facilities in hand already, and because we're using so many of the systems that have already been used, this testing process is much quicker. So if we can achieve these different milestones, here is the sensitivity and the spectral survey time that we will achieve. So on the left, you have your spatial spectral survey times. This is the time to survey 1 square degree to a certain noise level as a function of wavelength. And I told you before that we had a factor of 1,000 improvement in sensitivity, but for those of you who are paying close attention, you'll see that from Herschel Pax and Herschel Spire down to Origins on this plot is actually more like 1 billion times below that level. And that's because we have a factor of 1,000 improvement in sensitivity, but these big multiplexed arrays means that your fast mapping speed means that you can do surveys very, very quickly. And so that gives you a factor of 1 billion improvement as opposed to just a factor of 1,000 for the sensitivity. It gets even better when you're looking at the continuum mapping with Origins FIP. It goes down even lower. All right, so now that I've hopefully convinced you that this architecture is a robust, clear path for moving forward, let's think about the science that we can do with this new architecture. Let's hope it's good, right? Because you've already convinced that it's totally feasible. So let's see. So the first question is, how does the universe work? And this is all centered around us discovering our origins, where we come from. And this science question is really related to the coevolution of black holes, stars, and gas within galaxies. And with Origins, you're going to be able to watch this process happen across cosmic time, looking from the very early universe all the way up to the present day, and simultaneously measure the AGN activity, the star formation rate, and a lot of aspects of the feedback. So all these different processes that make a galaxy, that lead to potential habitability in galaxies, that lead to potential life, this is all things that we can observe simultaneously with Origins across millions of galaxies over cosmic time. No longer these tiny little samples of galaxies comparing this population and that population. We're going to do the full consensus of galaxies over cosmic time. And Origins fits in this beautiful window between James Webb and ALMA. You can see a galaxy rest frame spectrum here with some key diagnostic tracers such as AGN, feedback in green, or star formation in blue. And as you go from redshift of 0 through redshift of 2, 4, 6, and 8, you can see that many of these important diagnostic lines fall within the infrared. And because we're going to be able to map these contiguously, spectrally, all of that whole spectral bandwidth, that means that we get all of these diagnostics simultaneously. And because we can map so quickly, it means we can do it towards millions of galaxies. So Origins fits in this beautiful window in between what James Webb and ALMA can do. And I also like to think, James Webb is sort of our next step. We're going to a higher redshift. But if you think about, if you want to go deeper into the universe and further back, you have to go to even higher redshift. And that's what Origins will enable us to do. Side-by-side comparisons with the things we've been doing towards nearby galaxies with Hubble for a long time, with some of the most distant galaxies in the universe. One of the benefits of Origins is that we won't be confusion limited, and that's because of the spectral mapping. And so we have this nice animation here, which shows us today, redshift 0, Origins, and then mapping out across the different redshift bins. So because of the spectroscopic nature of the mapping, you can do this very quick mapping, but then you're not just getting this galaxy and that galaxy in some confused, picture with all of them together, you have this third dimension. You know the redshift, and so you can actually place them all at their different redshifts. And so you're measuring all of this 3D volume of cosmic space simultaneously. And that's, again, it's not just pictures of galaxies, it's their star formation, it's their AGN, and it's their feedback. Okay, here's a comparison of what origins could map. We've designed a couple of different survey options that we present in our final report, but I should have mentioned already, origins will be a geo facility, and so this is just to give you a flavor of how long different mapping strategies take. So to repeat, LSST, which is shown in the blue here, would take origin about 1,000 hours at 250 microns, and to look at WFIRST at 50 microns instead would take only about 1,600 hours. So we're talking about mapping out huge volumes of the cosmos, and again, not just one continuum image, 2D, the three-dimensional volume. I'm really excited for how this might revolutionize our idea of galaxy evolution, and it no longer becomes like butterfly collecting, right? We're actually going to do statistical samples of galaxies across the entire cosmic volume. All right, now coming back to the selfish questions, which of course interest me the most. How did we get here? This question is all about how do planets develop habitability? How do planets become habitable? And how did we come to be here? To do this, we're studying the trail of water. Again, very selfish beings we are. We are made mostly of water. We need water to survive. And so understanding the path of water and how it gets to planets is very important for understanding our cosmic origins. So origins enables us to follow the whole trail of water, which has not been possible before. If you're wondering, well, people don't seem to care about water because I don't hear a lot about it, it's because it just hasn't been possible before. So origins will really open up a new discovery space in understanding our origins through this water trail. From protostars in the ISM, where the water content is there, down to protoplanetary disks, debris disks, and finally into our own solar system, we'll trace that trail of water. And this is enabled simply by the wavelength range that we cover. So if you look at the number of cold water lines, which are shown here on the x-axis as a function of James Webb, origins, and ALMA, you can see that by far small studies have been done here before, but origins will totally revolutionize what we can do in water. To show an example of this, we have a video tracing water emission in disks. Maybe it's not working because I changed to Keynote. I'll switch back quickly. Okay. Okay, hold on. What's that? It was okay for a second? Okay. Interesting. Okay, so now we're looking at a protoplanetary disk here, and then we're looking at all these water lines that we can access with the mid and far infrared. Now you're tracing out different transitions of this water line and seeing what part of the disk you're tracing. So you had the snow line originally. Now when you go to this higher excitation line, you're looking at an outer part of the disk. And then we're going to go to even higher excitation, and we'll see an even outer part of the disk. So with these this huge forest of water lines here, you can trace different parts of the disk. You can trace how the water is where the water content is in these disks and what its properties are. This simulation is now showing the inclination variation. So now it's switching the inclination angle. And you can see that the spectral lines here are varying as well. So actually by tracing the shapes of these spectral lines, you can trace how the spectral lines are, how the disk is inclined, and different properties of the kinematics. Okay. Origins also has this unique tracer of HD. HD is fabulous because CO is terrible. Can anyone think of any reasons why CO is terrible? CO is terrible in disks. right? So CO is especially terrible in disks. It's not terrible everywhere, but it's terrible in disks because it gets frozen out. There's all kinds of complicated chemistry. And if you're trying to trace the total mass of gas using CO in a disk, you're mostly just tracing abundance variations in the CO, and that's going to cause a huge level of uncertainty in your gas masses. HG, on the other hand, is much more simple chemically, and you can easily trace the total mass of disks. And Origins, because of its incredible sensitivity, will allow us to trace these to very high sensitivity. So this is showing the different disk gas masses that we can trace, looking in order of Jupiter masses. So one Jupiter mass is here, and we can trace all the way down to a Uranus level of Jupiter mass within a protoplanetary disk. So we're not talking about measuring the gas mass of one disk or two. We're talking about measuring this for thousands of disks. So again, just totally revolutionizing all our ideas about planet-forming disks. One other big mystery in our cosmic origins is related to the origin of Earth's oceans. You can see the protosolar nebula, where the Earth was formed, sort of has this pretty consistent D to H ratio. Jupiter and Saturn and Uranus and Neptune sort of fit somewhere within that, and the Earth is substantially above that line. And so we think that this means that the Earth's oceans did not come from the protosolar nebula where it stood, but that it might have been enhanced by some comets within our own solar system. And understanding the origin of our own oceans through measuring this D to H ratio is critical to understanding. And we all love oceans, so it's like, think of where the dolphins came from. Maybe the dolphins came from comets. I think that's a really fun idea. Right now, it's hard to tell because we only have very small number statistics, and we can really hammer down on this and get over 200 comets and asteroids, really hammer down on what the D to H ratio is as a function of location in the solar system, try to figure out where our oceans came from. This just gives an overview of the different things that we can do with the water trail. Again, going all the way from prestellar cores, protostars, disks inner, disks outer, ice mass, debris disks, and comets, and how Origins compares with previous facilities. The purple bar is sort of showing the expected range, and then each of the previous facilities, James Webb, Herschel, and Spica, are shown by these symbols and where Origins is in comparison with these. All right. Finally, are we alone in the universe? If we answer this question, life as we know it would never be the same. And we're presenting one of the first tests of biosignatures towards other planets on a systematic level and looking at a number of different planets. If we don't detect anything, we're still talking about transformative science, looking at weather and temperature and the content of other atmospheres. But just pause for a moment and imagine if we found biosignatures towards another planet, what that would do. How would that make you feel? It'd be pretty exciting. So to do this biosignatures study, we're going to be looking at the transmission spectroscopy around planets, around M dwarfs here. So the M dwarfs, the planets will be transiting the M dwarfs, and then when they pass in front of it, you can look at the difference in the spectra and basically get the transmission of the atmosphere by the star passing through it. And so you can see the difference of the star without it and the star with the planet and figure out the spectral lines that are there. And there's some combinations of molecules, which we'll talk about more in a second here, which are thought to be pretty clear indicators of life, though of course it's always discussion, but it's certainly a very tantalizing possibility. This video will show basically, we're going to have to look at many, many transits. This is an extremely difficult and challenging technological problem. And so you can see as we go to more and more transits here, you can see the noise coming down here. You can see all these critical lines here that start to come through. So when you get to 40 transits, you can have definitive detections of a number of these important biosignature tracing molecules. Sorry, biosignatures is a very specific word. Not all these are biosignatures, only a couple of them in combination are biosignatures, but they're all interesting for life. They're all like organic chemistry. Why M dwarfs? Well, for one, we can. For two, they're the most common stars in the galaxy by a long shot, and so searching for signs of life, understanding the planets that exist around these stars, actually will just tell us a lot about the planet population of our galaxy as a whole. And just because of the nature of these small M dwarfs, it makes it much easier to detect these transits. You have larger transit depths. The planets are closer to the habitable zones, so you actually can get 4D transits pretty easily. And so all the planets that we're going to look at are in the habitable zone of their M star. And there's already some planets like this that are known. So this is looking at 0.8 to 12 microns here and the different molecules that are here. So all of these things are interesting indicators. I mean, if we discover any of these in another planet, that would be very interesting. But at least from what I understand, only a couple of them are more clear indications of life, and these are called biosignatures, and that's pairs of molecules, ozone and methane, or ozone and N2O. Those two things together are not found in equilibrium systems. If you have one, it should be destroyed by the other, unless there's some process that's constantly creating these molecules. And on Earth, the processes that are creating these molecules are life. And so the reason that we have these molecules in combination in our own atmosphere is purely a result of life. So those combinations of molecules are what we're looking for. Those are called biosignatures. Again, not purely definitive that there has to be life there, but it's a very strong sign. So all of these molecules would be interesting, but the biosignature pairs are really the key to being able to say that there's a decent chance that there's life there. So as I've mentioned, this is a very challenging technological problem, but we have a clear plan and a path to move forward that ends up with having biosignature measurements towards 10 temperate worlds. So we start by finding the best candidates. So we find at least 28. We do transit observations. We find planets that have clear atmospheres that we can see down and actually see the atmosphere of the planet itself and not just the surface. And then we do a couple of more tests to try to figure out if they're temperate. These are already planets that are already in the habitable zones, right? So we've already ruled that out. So we're just narrowing down to find the best candidates possible. And then we end up with 10 where we can look at these biosignature combination molecules together. So James Webb will do some of this, but not the biosignatures. That's very important. And it will also be very difficult for James Webb. So we have equivalent of 60 transits per telescope for James Webb on the top and origins on the bottom here. So you can see that within 60 transits, James Webb can detect CO2, maybe CO, maybe a little bit of water. Actually, I'd say that's pretty difficult. But these biosignature pairs here are completely within the noise floor. Whereas with origins, with the same setup, you can start to see these molecules, and they come out of the noise floor. So you have your ozone here, you have your methane lines here, for example. So that'd be one biosignature tracer. And this is why that noise level, that 5 parts per million, is so key. And just, I didn't realize this at first, and I really like it now that I realize it, but this black line is actually our Earth spectrum. So that's cool. So that we'd be able to detect Earth within 60 transits. But not because it's an M dwarf, so you know what I mean, though. But like the atmosphere of Earth. Okay, yep. Finally, to the discovery of new phenomena. I think all of these questions are important, fundamental, and really meaningful ways for us to move forward in astrophysics. I think everyone in the community, there's something for everyone here. And especially, I'd say the discovery of new phenomena is what excites me the most, because it's just like the mystery, right, of what might be out there is always very tantalizing. And so there's a long history of when you look somewhere new, when you do something different, you find the things that you don't expect. So from IRAS and Spitzer and Herschel, we've seen this process over and over again, discovering new things in these different regimes. But the new sensitivity threshold enabled by origins is a different scale. So I think that we are guaranteed some discoveries, but I think that with the crazy improvement in sensitivity, we're guaranteed more discoveries than a lot of these before. Besides IRAS, I guess that was like first time looking at the infrared. Okay. All right. A lot of community science is also enabled by origins. These are just some of the projects that we're really excited about that we can't fit into like the basic idea of the project, but we have something like, how many white papers are submitted by the community? around 50 white papers from the community on different science cases we can do with the Origins telescope. Highlighted here, we have looking at H2 mapping in nearby galaxies. You could do a huge field here in only 12 hours. We'll cover a really important scale in our own galaxy, looking at dust polarization. We usually have Planck and then ground-based, and there's really nothing in the middle if you want to connect the magnetic field from large scales to small scales. Something like Origins could have meaningful impact. You'll hear from Will later about this really cool time variability protostellar accretion. That's another thing that I think the discovery space of the time domain in far infrared holds a lot of promise. And that's something that hasn't really been explored yet. And Origins can do that, and it's enabled by the survey capabilities. Finally, as a reminder, this is a mission that's from the community. These huge working groups working with us gave us all these ideas, these white papers. They said, we asked them, what do you want? What do you want to do in the far infrared? They told us, and we built a mission around it. And so we have to thank all those hundreds of scientists and engineers around the globe who've helped us to develop these science cases and the whole instrument and architecture package that has this very exciting but very feasible and safe mission. All right, and as I mentioned before, this is a geo observatory. It's for everyone. It's not for specific projects. The community will decide what it does. Here's what we've presented as the most important ideas from our community so far, but the community will decide. So as a final summary, Origins opens up more discovery space than any other proposed mission right now. Origins is the only one that offers a factor of 1,000 improvement in discovery space, and it's doing it in a very safe, very reasonable way. Everything about it is robust, it's tested, you have very few deployments, and it's all very technically mature. We have a few technical hurdles to surpass, but we have a clear roadmap towards them, and all signs indicate we are good to go. So, inspired by Alex, we're pretty much ready to select Origins, move forward. Thank you very much.